Alright, so it's time for problems now. I've chosen NCERT examples, some solved and also unsolved ones we'll be doing. But yeah, and to understand, if you do NCERT problems in the beginning, that's really going to help you. Even if you're preparing for some competitive exams, make sure that you're doing at least NCERT examples first, because many a times you may think that who would solve NCERT examples, I'd rather do the problems from our handbook or the competitive books that are available in the market. But trust me, many a times we end up underestimating NCERT questions. They start from basic and eventually they have some really good questions in NCERT. So doing NCERT problems in physics is very important. And you know what they say about problems, right? So if you've not really studied physics, if you're not able to solve problems, right? So yeah, it's really important problems, and there's only one thing about being able to do good in problems. It's only doing a bunch of them, a lot of them, right? Yeah, so let's try this question. So we have a square loop of side 10 centimeter and resistance 0.5 ohm, okay, which is placed vertically in east west plane. So it's placed vertically in east. Yeah, fine. A uniform magnetic field of zero point 0.1 tesla is set up across the plane in the northeast direction. All right, so we'll decide all the directions in a minute. The magnetic field is decreased to 0 in zero point 0.7 seconds at a steady rate. So initially the field was 0.1 tesla, and then that field is changed from 0.1 tesla to 0 tesla in zero point 0.7 seconds at a steady rate. Okay, determine the magnitudes and magnitudes of EMF, induced EMF, and current during this time interval. All right, so looks like this is a classic question of Faraday's law, because looks like by changing magnetic field from 0.1 to 0 in such some certain time, you're changing magnetic field. By changing magnetic field, the flux across whatever this loop, square loop that you have, is changing, and due to that changing flux you have EMF, and you can directly calculate induced EMF using Faraday's law. So let's approach it that way, right? So all you have to find is change of flux and then divide that by time interval for that much of change of flux, and then you have your EMF. Once you get EMF, current can be found out using Ohm's law. So that's going to be my approach here, and if you want to try now, you can just pause and try it now. All right, yeah, so let's do this. So we have to begin with a square loop placed vertically along east west direction. So I'll have to decide the east west directions now, right? So let's say this is my west and this all the way towards this is the east. So yeah, there goes. So basically this is your east, this is your west, and in this problem I'll not make a mistake of calling this as north. No, that is vertically up, that direction is vertically up. My north actually is directed inwards, so I'll try to draw north like this. So my north actually is something like that. It is basically, I hope you get the idea, right? So that's my north, and this basically right here is north, and this direction over here is south. So that's your north and this is your south, just to show that. Yeah, so you can't see really that, you can't really see that part literally. I'm trying to draw it like that. Alright, so you get east west south north, right? This south north actually is perpendicular to the screen right now and coming towards you. South is towards you, north is away from you. All right, fine, enough with that. You have a square loop of side 10 centimeters. This side is 10 centimeter. This is 10 centimeter. What else? Resistance, all the data I'll write here. Resistance of the loop is given as 0.5 ohms. All right, what else? Magnetic field, at least initial magnetic field, so I'll call it BI. Initial magnetic field was 0.1 tesla, and after a while we eventually made the magnetic field, so final magnetic field BF is 0 Tesla, right? So we changed it. All this happened in a time interval of 0.7 seconds. So we changed the magnetic field from 0.1 Tesla to 0 Tesla in 0.7 seconds. What else is given? Yeah, pretty much this, except for the magnetic field, which I still have to show the direction. Looks like look at the question carefully. They've said that the magnetic field, magnetic field is set up in northeast direction here. Alright, so let's find out northeast direction. Northeast would be somewhere between the north and the east, right? So not somewhere between, exactly between north and east. This will be your northeast direction, and that's the direction of magnetic field that they've established. How much is this magnetic field in the beginning? 0.1 Tesla, right? And when they say northeast, it's always equally inclined to north and east. How much is that angle? It's actually, if you are seeing it from the top, you'll see that these angles are actually 45 degrees each. So this is 45 degree, and even this is 45 degree, right? So that's northeast direction. All right, now what? All I need is to calculate initial flux, and initial flux, and of course final flux, and then change of flux divided by change of time will give me EMF. So let's calculate that, right? So we know that according to Faraday's law, so here goes solution. This is my solution right here. So according to Faraday's law, you don't really have to write all these things. I'm just writing it to show you. According to Faraday's law of EMI, induced EMF is basically, don't worry about the negative sign. Let's say I'm taking the magnitude, right? So change of flux, which is final flux minus initial flux divided by total time required, right? Actually, this is another way of writing. As we have studied, Faraday's law was actually this, d phi by dt. That is a small instantaneous change, right? This is for a large change. So change of flux by change of time. Anyway, enough with that. Let's see. So induced EMF is going to be equal to, let me write the expression for final flux and initial flux, right? Or at least I'll try them somewhere else, and then I'll come back to this. Looks like, look at this, your magnetic field is so much, and square is of side 10 centimeter. 10 centimeter actually in meters is 0.1 meter, right? So yeah, my flux, at least the initial flux, would be, what's the expression for flux? B, the magnetic field, into area into cos of angle between the magnetic field and the area vector. Now actually, if you see here, the area vector is along north. This is your area vector. Why? Area vector is always perpendicular to the surface itself. So the red little north side is your area vector, and this is your field vector. This right here, the magnetic field, is your field vector. And what is the angle between area vector and field vector? 45 degrees, right? So yeah, I'll be using cos theta as 45. So let's calculate that. Initial flux would be, magnetic field is 0.1 Tesla, at least initially. How much is the area? 0.1 squared, which is 0.01, into cos 45. Cos 45 is 1 by root 2, right? So your initial flux is 10 to the power minus 3 divided by root 2, right? Weber, by the way, is SI unit of flux. Also, let me calculate final flux, and I'm thinking final flux is 0 because finally magnetic field became 0, right? So final flux clearly is 0. So if I substitute these values in the expression here, so magnitude of 0, the final flux, minus 10 to the minus 3 by root 2 divided by delta t. How long did we take for all this to happen? 0.7 seconds, right? So it will be like 0.7 seconds. Okay, all you have to do now is simplify this to get EMF. Once you get EMF current, you will find in no time. So induced EMF is, I don't know, don't worry about the negative sign because of the magnitude. Do not worry about the negative sign because you're taking magnitude. Alright, so 10 to the minus 3 divided by root 2 into 0.7, which is 7 by 10. So 7 into 10, you can just simplify this and get the answer for EMF. So EMF is, I'll leave it at this stage, which is 10 to the minus 2 divided by 7 root 2 volts. So that is your EMF value. So EMF across the loop developed is so much. I'm sorry for, yeah, get the idea, right? Now for the current part, current is pretty simple, guys, right? Once you get the expression for EMF, all you can do is use Ohm's law and get the expression for current. So according to Ohm's law, if I use Ohm's law, you don't, again, like I said, you don't have to write all this. Even if you're writing board exam, you don't really have to mention which law it is that you're using. You just write the formula. Make sure that if you're writing the answer in descriptive way, make sure that you're writing formula. No need to mention which law and all that. Yeah. Anyway, so yeah, current is EMF divided by resistance. So let's get this done quickly. Right, 10 to the minus 2. EMF is 10 to the minus 2 divided by 7 root 2. Divided by resistance, or into 1 by resistance. How much was the resistance? 0.5. Yeah, so 0.5 is half, right? So you'll get 1 by 2. 2 goes to numerator, and your answer will therefore be I'll write it here, the answer. Current therefore is root 2 into 10 to the minus 2 divided by 7 amperes. So that's your current. Pretty simple, straightforward question. But yeah, remember, usually sometimes here it looks like that they had given a big change, right? So you did final flux minus initial flux. If the flux is, sometimes they'll give you the expression for field. All those questions we'll see in higher versions. Don't worry. So I hope that was that. I hope you understood that. Let's try this question now. All right. So we have, let's see what we have here. You seem to have a circular coil of radius 10 centimeter and 500 turns. So I have a circular coil this time. Yeah, 500 turns, and resistance 2 ohm is placed with its plane perpendicular to horizontal component of Earth's magnetic field. Okay. It is rotated about its vertical diameter through 180 degree in 0.25 seconds. I'll explain all that. Yeah. Estimate the magnitudes of EMF and current introduced in the coil. Yeah. Where horizontal component of Earth's magnetic field is given to be 3 into 10 to the minus 5 Tesla. All right. Let's try this question. Right. So you have, to begin with, you have a circular coil whose radius and all that we'll mention in a minute. So we have this circular coil whose radius is 10 centimeter or whatever. Just to actually it's a loop, so it's a circular loop. I give you that it's a circular loop, right? But just to for some explanation reasons, I'll just fill this region with a different color. Oh my god, that's a bad color to choose. I'll just fill this region. It's making it worse. Forget the color, right? So yeah. So circular coil placed vertically, something like this, and the plane of the circle actually is perpendicular to the Earth's horizontal component of magnetic field, right? So let's say this is the horizontal component of Earth's magnetic field, something like that. You get the idea, right? So basically this is BH, horizontal component of Earth's magnetic field, which is given to be 3 into 10 power minus 5. All those things we'll use later. Yeah, radius and all that, expressions and all, we'll worry about that later. But let's see what is going on here in the problem. So yeah, you have the circular coil, magnetic field. Yeah, you are rotating this coil about a vertical axis. So let's say that axis about which you're rotating this circle is this. About this axis, you're going to rotate the coil now. You're going to rotate this coil. By how much? By 180 degree. So actually, if you rotate it by 180 degree, at the end of your journey, at the end of rotation by 180 degree, the circle will literally look like the same, right? Right now, since I've drawn a proper circle here, it's not like If you see my diagram or something like this for a circle, that would mean that the circle is not really placed on the screen. That would be a perpendicular circle, right? But this circle that I have tried to draw is actually lying on the plane itself. But once you rotate it, later on if you see after a complete rotation, once again you will see exactly the same circle, with exactly, so except you will be now seeing after a 180 degree rotation, you will now be seeing the other face of the circle. Like right now you are seeing this face, right now you are seeing this face, and what you're not seeing is the face behind. Later on you will be seeing this face, and then this face will go behind. I hope you get that point, right? That's what they mean by rotation of 180 degree. Yeah. Alright, so let's see. I'm going way too slow. Maybe I'm explaining things that I really don't even have to explain. Right, so be patient, and if you find these things difficult, of course you can skip through to the real problem solving part of this question. Alright, so yeah, so after rotation 180 degree this happens. Alright, so let me just mention the given data at least, right? So you have, what all do we have? We have a circle of radius is given to be 0.1 meter. Always go for SI unit as if quickly possible. Number of turns they have given, interesting. We'll see what that does. Number of turns is 500. Resistance of this coil is 2 ohm. What else? Time required for that amount of rotation is 0.25, or I can write it as 1 by 4 second. Right? What else? Magnetic field. The horizontal component of Earth's magnetic field given in that region happens to be 3 into 10 to the minus 5 Tesla. This is the magnetic field you have in that region. Alright, so in this case, first of all, looks like they are asking you to calculate the value of EMF, right? So you should see, look at this. Arrive at the magnitudes of EMF induced and current induced. First thing you should be asking yourself, is the flux changing? Is the flux changing? Actually, I think the flux will in fact change, because right now, guys, now focus, now pay attention. Right now the area vector is like that. So what's the angle between the magnetic field and area? 0 degree, right? After a while, before you complete it by 180 degree, before you completely rotate it by 180 degree, somewhere in between this, your circle should look something like this. It will be, you will have rotated it by 90 degree, and it would look something like this. It would look something like this, and your magnetic field will then be actually like that, right? So this is a magnetic field, and in this case the area vector has now rotated. Earlier area vector was in this direction, but after having rotated it in this direction, the area vector actually has sort of gone this way. Area vector is now here. Later at the end of 180 degree, area vector will be towards you. So you're getting the idea, right? Area vector initially was away from you, then it is to the left, and then it's like this because you're rotating. Alright, all that we'll do later. Let's focus on the present situation. Yeah, so when this happens, what's the angle between area vector and the field vector? 90 degree, right? And then finally, what's the angle between area vector and field vector, which is still in that same direction? 180 degree. So looks like clearly the angle between area vector and the field vector is changing. So due to change of angle, the flux is actually changing, and you know that if the flux is changing, you always have hope for induced EMF. So let's see that. So for that, all you need to do is find the flux, right? So my expression is going to be EMF is change of flux, which is final flux minus initial flux divided by change of time. And once you, like I said, once you get the EMF, current you will find in no time. Alright, let's focus on that. I'll try to get the expression for final flux, for initial flux first. Initial flux would be magnetic field into area into cos of angle between field and area. Alright, so in this case, how much is the magnetic field? Given as, yeah, it's the Earth's horizontal component of magnetic field itself, which is 3 into 10 to the minus 5. So 3 into 10 to the minus 5. Area is pi r squared, right? So it's a circle, so area would be pi into r squared would be 0.01 because radius is 0.1. Cos theta, look at this is, we are at this situation where area and field are in same direction, so angle is 0 and cos theta is going to be 1. So this into 1 is the same thing, except one thing I have not written so far is that actually with the number of turns being n, the flux expression changes. It becomes, the total flux becomes n times ba cos theta. So I'll have to multiply that also. N is 500. So this is going to be your initial flux, which is, I'll keep pi as pi itself. So you'll get initial flux as 15 pi into 10 to the minus 5 Weber. Final flux, you know, final flux nothing changes except for cos theta. Earlier theta was 0 and now theta is 180 degree, because at the end of the journey your area vector is now pointing towards you, and the field vector, field vector is still, you know, in that direction. The horizontal component of Earth's magnetic field is still in that direction, and now the angle is 180 degree. So only that thing changes. So with the cos 180 you will get final flux to be minus of this value, which is 15 pi into 10 to the minus 5 Weber, right? But when you subtract this you will get 2 times the value, right? So now let's calculate this. EMF is final flux, which is minus 15 into 10 to the minus 5, and initial flux, so minus of this will become plus only, right? So you'll actually be adding them. So your total change of flux would be 30 pi into 10 to the minus 5 Weber divided by time taken was actually 0.25 seconds, so which is 1/4, right? So 1 by 4, so 4 goes to numerator. So your EMF actually is 120 pi into 10 to the minus 5 volt. I know it's not scientific notation, this is not a proper notation, but yeah, answer will be that. You can simplify it further if you want to get the exact value. Alright, let's calculate current now. Current, pretty simple. Current is nothing. Once you get this, current is basically going to be EMF divided by resistance. So current would be 120 pi into 10 to the minus 3, 10 to the minus 5 divided by how much of the resistance? 2 ohms, so 2. Current will therefore be 60 pi into 10 to the minus 5 amperes. So that's the expression for current, right? So current is so much, EMF is so much. I hope that that was helpful. The trick is to understand the rotation and change of flux. Even though initial and final positions, if it's a ring, they look exactly the same, there is actually a change of angle by 180 degree. So yeah, and that change of angle led to change of flux. Just a little note I want to make here. See, actually flux can be changed in many ways. Magnetic flux, since this is the expression for, sometimes you write delta S, sometimes you write A for area, so I'll just go with A. NBA cos theta, that's the expression for flux actually, N being number of turns. So flux can be changed by changing any one of the 4 variables. So in the previous question, the first question I discussed, there the flux was changing due to change of magnetic field. That's what was happening in question number 1. Right now in question number 2, it is changing due to change of angle. Maybe in some other question we'll be, you know, changing the area. One such nice question is, maybe I'll discuss in one of my videos, is that you take a long wire, first you bend it in the shape of a circle, now you cut this one, just cut it and then convert it in same wire you'll take and you'll change it in the form of a square, right? Did the length change? No, same wire, first you had bent it in the shape of circle, now you have taken the same wire and you have suddenly changed it from circle to square in, let's say, some time t. So we'll mention that time in the presence of field, of course, in the presence of magnetic field, uniform magnetic field B. So here actually area is changing, circle to square. Definitely, even though circumference is same, the area will be different. So there in that question, in this question that I'm trying to discuss, actually I'll discuss this question in detail in one of my videos. There it is changing by number of change, the flux is changing due to change of area. So you can basically change the flux in many ways. You have to identify first of all whether the flux is changing, and when will the flux be changing. If any one of the four variables that I mentioned are changing, then flux is definitely changing. Alright, enough with that. Now let's try this question. What do we have here? A metallic rod of length 1 meter is rotated with a frequency of 50 revolutions per second. Something else they're rotating. Okay. With one end hinged at the center and the other end at the circumference of circular metallic ring of radius 1 meter. Okay, something is going on here. About an axis passing through the center and perpendicular to plane of the ring. All right. A constant and uniform magnetic field of 1 Tesla parallel to the axis is present everywhere. What is the EMF between the center and the metallic ring? Is the question. Okay. Okay. Let's do this. Alright. Don't worry. It's nothing this. Right. So you have a metallic rod. I'll go with the way they've started question. So first of all I'll take a metallic rod. So let this be the metallic rod we have. Where is the metallic rod? Of length 1 meter. Great. So, oh, this is too long of a rod. Let's, yeah, let that be the metallic rod. Alright. So green color metallic rod of length 1 meter is rotated with a frequency of 50 revolutions per second. Alright. With one end hinged at the center and other end on the circumference of a circular metallic ring of radius 1. Okay. So basically they're saying that this end is hinged, means it can rotate about this point. I'll make it solid, more solid. Yeah, this point right here. About this point it can rotate. Right, so one end is fixed at the center of a circle and other end at the circumference of a circular ring. So you are going to actually have a circular ring about which this metallic rod is rotating, something like this. That see, the pink color is the circle. So one end is hinged at the center of the circle and the other end is free. It can rotate about. It's touching and rotating like that. All right. If this is happening, and also there is a uniform magnetic field established in the direction of axis itself and perpendicular to this plane. So the axis you see is actually perpendicular to your screen. This axis is actually like this, guys. That axis they're talking about. I'll just draw the axis once. I'll try. Right. So this is actually your axis of rotation. This right here is your axis of rotation. They're rotating about this axis, right? And there is magnetic field along the axis itself. So magnetic field actually is perpendicular to this plane itself, right? So magnetic field lines actually are, you can go with bunch of dots or crosses, doesn't really matter. I'll go with cross, right? So this is the direction of magnetic field, uniform magnetic field in this region. I hope you get the idea, right? You can read that part once again if you like. The magnetic field is along the axis itself. Okay. And don't forget the green rod, which is what is going to rotate in this region. The green rod will be rotating in this region. All right. With some angular velocity, I hope they have mentioned that speed. Have they? No, frequency is given, so angular velocity can be easily calculated. All right, no problem. So I'll just to emphasize that, let's not forget the real character of this question is, main character of this question is this rod itself. So I'll just highlight that. This rod is what that really matters to us to solve this question. Yeah. So that rod is going to rotate. All right. In doing this, if the rod rotates anti-clockwise or clockwise, doesn't really matter. If the rod rotates, eventually it is going to go all around the circle and by the time it has completed a circle, it has in fact gone through a change of flux of all this region. This entire region it has been covering. This much will be the flux it has covered. The change of flux will be that this entire area of the circle. So that will be area, and through that area, in the presence of magnetic field, a metallic rod is rotating, so there will definitely be a changing flux. All you have to do is calculate that, right? So we'll go back to our Faraday's law, which says that according to which EMF is change of flux divided by time required for all that to happen. Here actually by the end of one revolution, this time will actually be period of rotation. This will actually be period of rotation, which we already know. We use the symbol capital T for that. We already know is 1 by frequency, right? So 1 by frequency will give me period of rotation. So I already have the denominator ready. We have to work on numerator. Let's see. So induced EMF is going to be equal to change of flux. Yeah, change of flux will be actually the magnetic field into area. That's all. The area of the circle into magnetic field divided by 1 by frequency. This will be your answer, right? So let's simplify this. How much is the magnetic field? Now only thing you're left with is to calculate the remaining part of it. So I'll just simplify the magnetic field into area. Actually I can write it as pi r squared. R itself is nothing but the length of the rod. 1 by f. I think I can write 1 by f as, f gets multiplied here itself. Fine. So induced EMF is going to be equal to, see the one thing you notice, whenever frequency is mentioned in revolutions per second, if you can see this part, the top end, the left end top of the question, please look at of the screen, look at that. They have mentioned frequency in revolutions per second. Notice here again, once again, top left corner, revolutions per second. Whenever frequency is mentioned in revolutions per second, they have given the value of omega. Omega is always mentioned in revolutions. Oh my god, I'm sorry, big mistake. Whenever they say revolutions per second, they have given the value of, I'm really sorry, f, right? So this f is what they are mentioning if they mention revolutions per second. And if the question say radians per second, then they are mentioning value of omega. So yeah, actually what is given in this question is f only. Yeah, let's calculate this now. So your answer is going to be, induced EMF will be, is there something missing? Nothing. So b pi r squared f, right? So magnitude of B, how much is the magnetic field? 1 Tesla. So 1 into, how much is pi? I'll just keep it as pi only, pi. Alright. Radius squared. How much is radius? 1 meter squared. So which is again 1 into the frequency, 50 revolutions per second. That is F itself. So you can just write 50 there. So induced EMF will therefore be 50 pi volts. 50 pi volts is going to be your answer. But one small thing I want to mention here, let's evaluate this a little further. If they had given in terms of omega instead of frequency, if the question was mentioned in terms of angular velocity, then you can in fact write f in terms of omega. We have this expression. Actually problem is done, but please listen to this part. You have this, that angular velocity omega or angular frequency can be written as 2 pi times the frequency itself, or you can just replace that. So omega by 2 pi. If you replace that, you will get the expression for EMF in current situation as B pi r squared. Those things remain as such. F can be replaced by omega by 2 pi. So I'll just do that, omega by 2 pi. Pi gets cancelled. You are left with EMF equal to B omega r squared divided by 2. This right here, guys, is an expression, if you can, to be remembered. It's good that if you remember this expression. This is the EMF in case if a rod of radius r or length L, I'm sorry, if a rod of length L, what am I saying? If a rod of length r, so length of the rod becomes the radius of the circle. So if a rod of length L, rod of length r, whenever I say length, naturally L comes out of my mouth, right? Yeah. So rod of length r is rotated with an angular velocity of omega in the presence of a uniform magnetic field of field strength B, then EMF is given by this expression. Okay, so I hope that if you can remember, please remember that expression. And anyway, if you don't remember, you can always start from the basic and go through these steps and you can get the answer. Fine. Alright, so there is one more question I had planned to discuss. This question right here, example 6.8. It's really the best question I could discuss so far. But this video is getting longer, so I'll discuss this question and other questions in next video. Alright, thank you.